when the angle theta, my dear student, is very, very small, now the torque must be equals to mgh. This could represent the torque. Now, since the perpendicular distance from G to the vertical through O is h sin theta, as we know that after dissolving, let us take and try to dissolve here, but form a result which is the horizontal here. This could be the opposite, and also we have the hypoadjacent. This adjacent is represented by the vertical line. Now, if we try to dissolve, we could obtain that. The sin theta could be obtained from Sotoka here, which is equal sin theta, which is equal to opposite divided by the hypotenuse. But we know that as we observe here, the opposite must be equals to the horizontal line, but also adjacent hypotenuse must be equals to h. Now, if we try to resolve here, we must obtain that the horizontal line here must be equals the horizontal line must be equals to h sin must be equals to h cosine theta, but the horizontal line must be equals to h times sin theta, while the vertical axis must be equals to h cosine theta if we try to dissolve here. But as we see that but sin theta must be very, very small. It must be very, very small. Now it must approximate with the angle theta. Now we should say that when the angle theta is very, very small, now this sin theta must be approximately to the angle theta. This is what we try to observe here. Then we could say that if it will be like that one, if it will be the angle very, very small and the approximate with the sin theta, now we could say that the torque, as we know that the torque is obtained by two equations. The first one, torque must be equals to the angular to the moment of inertia, then we times by the angular acceleration. Also, torque must be equals to mg to negative mg h sin theta, but the sin theta approximately to theta. Now we could say that when we equate this torque, we obtain that the moment of inertia times the angular acceleration must be equals to negative mg h times the theta. So hence alpha is equal to negative mg h over I theta. Now if we make angular acceleration as the subject, we could obtain that we should make it by dividing by I throughout, and if we divide, we obtain that therefore the angular acceleration here must be equals to mg divided by negative mg h theta. This is what we obtain here. But for the simple harmonic equation, the angular frequency must be the angular frequency of the small amplitude oscillation of a compound pendulum is given by this one. So if we recall from the angular acceleration, now if we recall from the simple harmonic, for the simple harmonic we tried to demonstrate the formula of obtaining the angular frequency, the angular velocity, by recalling that angular frequency for the symbol pendulum must be equals to mgh divided by L, radical of mgh divided by L, my lovely students, here as we try to observe. So now we should say that if we see this angular acceleration, angular velocity, which is equal to radical mgh divided by this L, which our this I. This is I as we try to observe here. This could be equals to I. Now let us come up and recall the frequency, the period of oscillation which is represented by T. This period of oscillation which is represented by T, we know that this is given by taking 2 pi, then we divide it by the angular velocity as we try to observe here. Now we could say that the period which is equal, the period of oscillation is equals to 2 pi, then we times it by the radical of the angular acceleration of the moment of inertia, then we divide it by mgh as we try to observe here. So therefore, we should conclude by saying that for a compound pendulum such as a rod, a disc, and also a lamina, the period T is given by this formula. So if we come up and recall for the compound pendulum, now we say that the angular, the period of oscillation for the disc, also the uniform rod and the lamina, it could be given by taking the 2 pi, then we multiply by the moment of inertia, the radical of the moment of inertia divided by the mgh. And now this will be our formula of obtaining the period of oscillation for this compound pendulums as we observe here. Now we should allocate this equation B the equation number 66 for our first topic here. So if you will be asked to identify the formula of obtaining the disc, the compound, the period of oscillation for the compound pendulum like this rod, this lamina, and also this disc, it could be given equals to 2 pi times the radical of I divided by mgh. Now, this I is a rotational inertial about the axis of suspension. Kwa yule I tutamuita ni rotational inertial. Ni rotational inertial. Tumisi kwamba when the body try to rotate on horizontally for the compound pendulum, it could give us the rotational inertia about the axis of the suspensions. And the M here could be equals to the mass of the compound pendulum. Kwa huyu M atarepresent mass of the compound pendulum, while of the compound pendulum. But if we use the parallel axis theorem, if we use the parallel axis theorem, we know that I must be equals to M, then we times it by h square. We add it by the k square, where k represent the radius of gyration as we observe here, my dear students. So we can say that this could be our equation number 67, which represent how we get the moment of inertia for the parallel axis theorem. So after this one here, let us look for a solid sphere. So for a solid sphere and the cylinder here, the torsional of a solid sphere or a cylinder, the period can be expressed as this one. If we recall for this solid sphere and also a cylinder, now we get the period of rotation, the period of oscillation as t equals to 2 pi, then we times it by the torsional inertia divided by this c. This c represents the torsional constant. We imagine that we put mgh as the constant, then we are obtaining that t must be equals to 2 pi times the times the radical of y divided by c here. So my dear student, here for a rolling motion of a solid and a cylinder on an inclined plane, the period can be obtained by this one. So if we leave for the torsion, now let us go and see for the rolling motion. Now we assume that we have the rigged body. That rigged body trying to roll, undergo a rolling motion. Now on an inclined plane. Now we could say that we get the period of oscillation by taking 2 pi, then we divide by r square plus k square, then we divide by 2g h. As we obtain this, could be our formula for when the body rolling, when the body rolling on an inclined plane. This will be our equation number 69, and we should write in a good way that t must be equal to 2 pi radical of r square plus k square divided by 2gh. This is our force equations, our 69 equation, where h should represent the height of an inclined plane, and also r represent the radius of the rolling of the object, and k could be equals to the radius of gyration. So by saying that this is the end of our session here, now I would like to invite you again for another session. I wish you all the best.